Now let's consider all of the possible effects that the leading coefficient A has on the shape of the graph. In the base case where the absolute value of A is equal to 1, and we use this absolute value here just to indicate that what we're talking about is the overall magnitude ignoring the sign. So this covers the A equals 1 and the A equals -1 cases. We don't have any stretching or shrinking of the parabola. It's the same exact shape as y equals x squared, but it is repositioned somewhere else in the plane, and it may be flipped. It may open up, it may open down, but the basic shape is the same. This is the shape of y equals x squared. This is the shape of y equals -x squared. We have only shifts, so the graph is only translated to somewhere else in the plane. If we have a leading coefficient that is in overall magnitude greater than 1, then we have what we'd call a vertical stretch. And in the case of a parabola, the graph appears more narrow if it is stretched vertically. But it's still true that if we have a positive leading coefficient, like this could be y equals 3x squared, for example, then the graph will open up. And if we have a negative leading coefficient, so this, for example, could be something like y equals -3x squared, then the graph will open down. If we have a vertical shrink, that is where the leading coefficient in overall magnitude is less than 1, so it will generally show up as a fraction. It could be a decimal value, but it is something smaller than 1. Then we have a graph that is vertically shrunk and it appears wider, almost as if an elephant came along and just sort of stepped down on it. You would notice that it widens out to accommodate that vertical compression. So this might be something like y equals 1/2 x squared and y equals -1/2 x squared. So positive leading coefficient gets us happy graphs. Negative leading coefficient gets us sad graphs. Putting this to use, let's look at a function here. We see that the leading coefficient of this is +3. So already we know that the parabola is going to open up. It's going to be stretched vertically, and so it's going to appear a little bit more narrow than our usual y equals x squared. But we still need to get a few points plotted accurately. Here's where the 1, 2, 3, 1, 4, 9 pattern comes into play, right? These are the values that we use in order to point plots relative to the vertex on a quadratic function with no stretching or shrinking. So this is what we would see in the case where the leading coefficient is equal to 1. If we take the leading coefficient of 3 and multiply it by all of these y values, then we'll get the pattern that applies for this particular function. So instead of 1, 4, 9, we now have 3, 12, 27. Now that 27 is almost definitely not going to fit on my grid, so I usually just ignore it. I'm definitely not going to rescale things to fit that point. But the 3 and the 12, there's some hope. At least the 3 should fit, and the 12, sometimes it fits, sometimes it's just a little bit off, but we can still sort of use where it's supposed to be, even if it's a little bit off, in order to get the shape of this parabola correct. So we're going to use this pattern again to draw the graph, but we will just have to modify it a little bit. We still start by finding the vertex. This is again in general form, so I need to use the vertex formula. I'm just going to go through that real quick. Go ahead and pause right now and find the vertex just to get some practice, and I will fill it in just a second. So using the vertex formula, I get a vertex of 2, -4. I'll go ahead and plot that vertex right here. Now I am going to use the information from my 1, 2, 3, 1, 4, 9 pattern in which the 1, 4, 9 is scaled by the leading coefficient. So from here I'm going to plot the point 1, 3 relative to the vertex instead of relative to the origin. So I'll go right 1 and up 3 and I get a point on the parabola. Now I'm going to plot the point 2, 12. Again, relative to the vertex instead of relative to the origin. Coming back to the vertex, I go right 2 and I go up 12, which is going to bring me all the way up to 8 up here. So it looks like I was able to fit 2 of those points, which is pretty good for a parabola with this much stretching and shrinking. Rather, this much stretching. I will draw in that line of symmetry again, just so that I can use it to more easily draw the points that are on the other side. Reflecting the magenta point and reflecting the green point, I get 2 more points on the graph, and I'm ready to draw in this parabola. Try to draw something that is smooth at the bottom, not pointed. You can see I didn't do a very good job of it right now. I'm just going to clean that up a little bit. And I think we'll have to settle for this graph here. It's a little easier to draw on paper than on this tablet. Try to draw something that is smooth at the bottom, that doesn't go into a sharp peak. But again, with a really narrow graph, it's a little bit harder to get that detail exactly right. So just remember that the graph is not a V shape. It is a rounded shape, and make sure that you don't draw something with perfectly straight lines going into a point at the bottom.